Olá, bem-vindas e bem-vindos. Eu sou a Mariana Almeida e este é o McKinsey Talks direto do estúdio da McKinsey em São Paulo. O episódio de hoje faz parte da série de Inteligência Artificial nos Negócios e vai abordar os modelos de aprendizagem profunda, ou Deep Learning Surrogates, que podem revolucionar a engenharia nos próximos anos. Esses sistemas conseguem aprender a partir da inteligência artificial como funcionam situações concretas para depois simular as variações. Assim, em vez de construir 10 protótipos, é possível construir um só, que vai servir para treinar o robô. E ele simula uma centena de variações em poucos segundos. A tecnologia tem um potencial grande em situações que exigem alta performance, como uma corrida de Fórmula 1, onde cada segundo importa. Na sessão de hoje, você vai conhecer o impacto destes mecanismos em casos que vão desde a otimização dos pneus de carros de corrida a aplicações em empresas de diversos setores. E para falar sobre esse tema, está conectado conosco o Jacomo Corbo, cientista-chefe da QuantumBlack, empresa de analítica avançada adquirida pela McKinsey em 2015 e que auxilia companhias a usarem dados na sua tomada de decisões. Por isso, a nossa conversa hoje será em inglês. Welcome, Jacomo. It's such a pleasure to have you here today with us.
Thanks very much. Delighted to be here.
Great. E também está aqui ao meu lado, no estúdio, o Pepe Cafferata, sócio da McKinsey em São Paulo e líder da QuantumBlack na América Latina. Olá, Pepe, bem-vindo, é um prazer tê-lo aqui com a gente novamente.
Muito obrigado, um prazer estar com vocês de novo.
Ótimo, então vamos lá. So let's get started. Pepe, why are we talking about digital surrogates? What are they? Are they similar to digital twins?
That's a great question, Mariana. This is coming from the world of very complex engineering problems, right? And up to now, there's a whole set of tools called computer-aided engineering, right? But basically what they do is they try to resolve very complex problems through mathematical equations through computers, right? And this process, it's very time-consuming for machines. It's very complex mathematical equations. It's very complex systems that have to do both simulation and optimization problems. And it's really important that these machines have enough computing power and enough speed to allow you to innovate at the fastest possible rate. And Jacomo will give some concrete examples now, but what we're doing is building deep learning models that can radically simplify and speed up the process of designing new products, optimizing value chains, optimizing logistics, and other applications like Formula One, like Jacomo is going to talk in a little bit.
Right, so we don't need this number of prototypes. We can do it with simulation.
We can do it with simulations. It's like a digital twin for very complex engineering problems. And you can do it at a much faster clip, which actually is a massive advantage of this kind of solutions.
Great. So, Jacomo, can you tell us some examples, like some concrete examples, please?
Yes, absolutely. Again, and this is something that applies very broadly. As Pepe was saying, at the core of a whole lot of engineering and a whole lot of engineering across, different sectors, different applications, whether we're talking about designing a wing, designing, a heat exchanger, designing the battery cell, the packaging for the battery in an electric vehicle, designing a wind turbine, designing an antenna. All of these things involve engineers who are going to be designing specific, elements of the geometry. We're going to be looking to optimize, therefore, different parameters around the physical design, the shape of the thing. And the shape of the thing has implications for performance. And the performance, as Pepe was saying, is something that's assessed through these computer-aided engineering tools, which are going to help you, which are going to run the physics basically that dictate the behavior of the thing, whether that's computational electromagnetic field simulation in the context of the antenna, or it's, just the flow of sound waves that are being propagated, or or air in the context of a wind turbine, or water in the context of a hydro turbine. But whatever these things, whatever the physics happens to be, it involves a whole lot of compute. It takes a lot of time, and what we're ultimately talking about here with surrogates is leveraging some of the latest advances actually in deep learning that allow us to build really high fidelity approximations of the multi-physics in ways that allow us to now really hyper accelerate our ability to be able to understand the performance of these things, and therefore to be a whole lot more sophisticated about how we search the design space, so how we search the space of parameters, which ultimately translate into the design of these things, whatever we might be talking about. And in the way of examples, again, this is something that applies so very broadly, but I'll name two. One is in the context of Formula One, and in Formula One, one of the most complex elements of an F1 car is the tire. And the tire dictates so much of a car's performance. It has implications for, just think of at the level of, grip, of course, and that grip is modulated by mechanical elements. It's modulated by the speed through turn, but that also has implications, for friction. And so if you just think about how the tire deforms and being able to model that with very high fidelity, that is a hard problem. It's a problem that hinges on solving multi-physics. And that's something that, the finite element analysis, which is ultimately the set of equations that are being solved when people are looking to analyze the performance of an F1 tire. That is something that takes a very long time to run, typically. We're talking about something which, takes on the order of about 15 hours or so to run. And when we, to give you a sense of the kind of accelerations that we're talking about in using a deep learning surrogate, we're talking about an acceleration from something that takes 15 hours to something that takes less than 1 second to run, right? So that should give you, and with very little compromise on the fidelity, the accuracy of the simulation itself. The other example that I would raise is something from the world of oil and gas. What that allows us to do in speeding up having a deep learning model, which is a pretty good representation, but is now much faster, is that it allows us to use the much faster representation to be able to be much more sophisticated about control. And the control now is something that has implications like really means lengthening the life of those assets. And, that has big implications from the point of view of maximizing the life of existing resources, maybe offsetting the need to start to embark on new exploration and new projects. And on the other hand, allows us to, be much more sophisticated about how we drive yield through the system. So those are maybe two different examples of the system. But again, these kinds of technologies are things that apply very broadly from design and engineering context all the way into operations.
So Jacomo, can you describe also the application of these techniques for operations problem, like steel manufacturing or logistics problem, right? And be able to use this simulation optimization tools for more operational or supply chain kind of work?
Yeah, absolutely. So there's other places, for example, where we can introduce, highly autonomous and maybe self-adaptive control policies in operations that, for example, in steel manufacturing. In steel manufacturing, this is something that we've been, we're tremendously proud of and been working on for about the last year. And this is a production planning process. So this is basically taking an order book and looking to ensure that that order book, is in terms of where a given order will be produced, what line it will be produced on, the sequence in which a given order will be produced. A lot of this has implications for delivery timetable, of course, but it has implications for waste, has implications for energy efficiency. And so it ultimately amounts to a very hard optimization problem. Now, there too, being sophisticated about how you solve that, that optimization problem hinges on having a high fidelity way to simulate the system as a whole. And I would say in that specific application, building the simulator has been one of the toughest challenges. But having built that, and if I think about like one of the hardest things to represent, it's been at the level of a lot of the operational constraints that have to be explicitly modeled or at least represented in that simulator. Those operational constraints are hard and fast constraints in many cases, or things that are really modulating cost or modulating whatever the metric of performance happens to be. And those things have to be captured and have to be captured to within a degree of accuracy in order to therefore say, I'm going to run an optimization. But the moment you have that, in that context, what we've built is a reinforcement learning bot, a deep reinforcement learning bot that now allows us to solve this optimization problem. And that's one that's worked, remarkably well. And maybe I'll just be specific of, I'll harken back to the last question with this specific example. This isn't something that is changing the planner's, life, if you will, right? It's not altogether changing their entire workflow, but it is buying them a whole lot of productivity and that whole team a lot of productivity, because instead of having to take the raw order book as their starting point for coming up with a plan, they're in a place where they can take what the reinforcement learning bot has given them as a plan and are only looking at tweaks and nominal variations therefrom, right? Which ultimately is, really accelerating how and changing ultimately how that team does work. I'll also say that, again, I don't want to underplay how important it is to have IT at the table to stand up a capability like this. This is something where a lot of the foundational services are set up on Kubernetes, and a lot of organizations, are just in a place maybe on what they're doing on-prem with their own clusters or what they're doing on the cloud that is allowing them to access these technologies. But it is, I mentioned Kubernetes explicitly because the moment you have that, doing a lot of what we've been talking about is a lot easier than trying to do without it.
So Pepe, Jacomo talked a lot about productivity, optimization, efficiency. So can you share some relevant numbers on efficiency or cost savings, please?
Absolutely. So there's savings from multiple perspectives, right? When you're doing product development and engineering, it's very important that you do that at a faster clip possible, right? Because in many of these industries, designing this is a very lengthy process, a very complex process, but also innovation is very fast. So take the example of Formula One, right? Every race, it's hugely important to win the championship. In sailing, when we did the America's Cup example, being able to innovate the hydrofoils at a faster rate than your competitors allowed them to win the America's Cup at the end of the day. So going from days to run these simulations to seconds is hugely important from a perspective of being able to resolve these problems. And as Jacomo was mentioning, to be able to have a real or almost real-time perspective of what's going on in the real life and the real world, right? So this is hugely important. That drives savings in the operations. It can be savings in your energy costs, of from 5 to 15, 20%, depending on your starting point, increases in yield of 5 to 15%, increases in throughput of similar ranges. So the impact of these systems can be substantial and significant, not only from a monetary perspective, but also from a product development and competitive and speed perspective.
Well, that's very relevant indeed. It sounds like there are so many potential upsides, as you just said. One thing I would like to discuss more, though, is AI's relationship with greener energy. What would it take to make AI greener?
It's a good question. I think that there's a lot of focus on AI in terms of questioning green credentials, in terms of a general concern around AI. It's a best-in-class models, a lot of state-of-the-art models moving to ever larger models, and these ever larger models have more hyperparameters, and just as a function of having more hyperparameters require more compute to train them. Like, I think a lot of people will know things like OpenAI's GPT-3 or Google's Palm or Microsoft's Turing NLG. These are all billion parameter models. We're now in a world where some of these parameters are trillion parameter models. The consequences here is that these things are not just very expensive for individual organizations to run, but also have heavy compute costs that translate into carbon footprints in their own right. They just consume more energy. I mean, I would contend that is a little bit of a red herring. And I say that with every sympathy for the people who worry about the cost of compute. And I would say that the cloud in the first place, where a lot of these models live, is in terms of where the energy is coming from. These are by and large some of the cleanest sources of energy. But I would also say that these things are increasingly offsetting compute. No one is training these large models at the same frequency that we train very small models. These things, by and large, are trained once, and then after that, only incrementally trained. And so, in many cases, they're run on inference and only trained relatively infrequently. Like, no one trains a GPT-3 model from scratch every single time. But I would say, in the context of everything that we've been talking about, the focus should be elsewhere. I think the thing that's really exciting about what we've been talking about here is an opportunity to leverage these, complex deep learning models. These are, in many cases, these are relatively large models, many layers, many hyperparameters, nothing like the language models that I cited, but still relatively large models on the whole. But what they allow us to do is to now help us optimize things that are going to be built out in the real world, operations that are, touching the real world, carbon intensive applications, things that are going to be tied to, the displacement of individuals and goods. And these are very carbon intensive processes. And just moving the needle in the way that Pepe was describing at the level of being able to just improve the efficiency of, I mentioned a hydro turbine before. You improve the efficiency of a hydro turbine by 1%. That is a huge amount of impact from the point of view of, from a carbon standpoint.
Jacomo, all that you're talking about is really exciting, and many of our viewers or listeners might be asking, but I'm kind of behind this curve. This is really sophisticated. It seems like the NASA to me. How mature do you need to be, and what are the first steps to get going on these technologies, right?
In the context of design and engineering, I think one of the most important things is to be, not to be experts or to have any capabilities for that matter around machine learning, maybe ironically, but to be relatively sophisticated and mature from the Pepe, from the dimension of what you were talking about at the very beginning, which was from a CAE perspective, from the point of view of how, a computer-aided engineering processes and what tools you have in place. So I think there's a bar of maturity at that level that you have, a pretty good foundation for how you run your design and engineering processes and what tools you have in place. And these are traditional tools, but still we're talking about a modicum of maturity there. I think the other dimension to think about is just from, and it's why I've mentioned it twice, just from an IT standpoint, I think it takes an IT organization that has a minimum of maturity at the level of cloud and at the level of manipulating certain technologies like Kubernetes. And again, just to pick on one, but that I think is a pretty good foundational element, and it is a whole lot easier to do a lot of the things that we're talking about here around advanced machine learning, whether we're talking about deep physics surrogates, whether we're talking about reinforcement learning, to do it on a relatively mature stack, trying to do this maybe in the cloud, but even for organizations that are not in the cloud for some of these systems, to do it therefore on-prem, but to still have a relatively mature stack. So that's another dimension here. And I think maybe another thing, just a little bit more broadly, is an organization that's really, highly committed to continuous improvement. And I think it takes an organization, and a number of people within the organization to say they're happy to explore and look at how technology enablement can change and help them improve on that baseline, which is set by their current way of doing things.
Thank you very much. Unfortunately, we are reaching the end of our session right now. So any final remarks you would like to share with our audience, Pepe and Jacomo?
I'll just say that this is a fascinating topic. It has huge potential. We are showing it already in very concrete applications, particularly around complex engineering problems. And I'm really excited about what you can do in product engineering and things you can do on the product design and product development phase. Knowing our clients in Latin America, the applications around operations and around supply chain are hugely, hugely exciting, right? Things like soybean crushing or oil refining or train logistics optimization, right? Things that are really complex to solve, that when you talk to your clients, they're like, this is a very complex problem, I have no way to solve it, or I have to break it up in pieces, which leads you to go to local optimizations and not global end-to-end optimizations. So I'm really excited that these things are coming to play. As Jacomo said, there are some preconditions that need to be in place. But if we have an executive team that is excited about exploring, we can bring these things together with our clients and add significant amount of value and innovation in these processes.
That's great, and cost saving and etc.
Exactly.
Giacomo, and you?
I mean, just echoing what Pepe said, I think one of the most exciting things about this is, and I think why we're excited about it is a little bit because the range of applications is so broad, and at the same time that this is technology that is really ready and production grade to be able to be deployed now. And that is a relatively new development. A lot of what we're talking about here, just at the level of software frameworks in which to build these capabilities, really didn't exist about 3-4 years ago. To the extent that the optimization opportunities are there, from design engineering into operations, and maybe with a view to trying to accelerate the sustainability transition, we're very keen to help organizations get on with it.
Thank you very much, Giacomo and Pepe, for joining us today.
Thank you.
We also are very excited, as Pepe said, to see what the future holds in this field. E muito obrigada também a você que nos acompanha em vídeo ou em podcast. Para entrar em contato com os nossos especialistas, nosso e-mail é McKinsey-talks@mckinsey.com. Você também pode enviar perguntas para o próximo episódio dessa série. Participe! A agenda completa do McKinsey Talks está no mckinseytalks.com. Lá você também pode conferir este episódio e também os anteriores em vídeo ou em podcast. É isso aí, muito obrigada e e até a próxima!